On March 8, 2025, astronomers at the Pan-STARRS Observatory in Hawaii flagged an object moving through the asteroid belt. Within hours, it was designated 31 Atlas. Within days, it became the most observed celestial body in modern astronomy. And within weeks, the questions surrounding it would challenge everything we thought we understood about objects in our solar system. What makes 31 Atlas different? Why are leading scientists breaking their silence? And what does the data we're not seeing tell us about what's really happening? The discovery came quietly, as most astronomical findings do. A routine scan of the night sky, a computer algorithm detecting motion against the stars, a designation sign without fanfare. 31 Atlas was initially cataloged as just another near-Earth asteroid, one of thousands tracked annually. Its orbit placed it firmly within the main belt between Mars and Jupiter, a region crowded with rocky debris left over from the solar system's formation. Nothing about the initial observation suggested anything unusual. The object was faint, distant, and unremarkable in size. For the first 72 hours, it was simply another data point in humanity's ongoing census of space. But on March 11th, something changed. Follow-up observations from the Very Large Telescope in Chile revealed an anomaly that would set 31 Atlas apart from every other asteroid ever studied. The object's albedo, its reflectivity, was fluctuating in ways that defied conventional explanation. Asteroids typically maintain consistent brightness as they tumble through space, their rocky surfaces reflecting sunlight at predictable rates. 31 Atlas, however, was dimming and brightening in patterns that seemed almost rhythmic. The variations weren't random. They followed a sequence. Music. Within the astronomical community, word spread quickly. Observatory networks across 6 continents began redirecting their instruments. The European Space Agency's Gaia telescope, designed for stellar cartography, was temporarily repurposed. NASA's Infrared Space Telescope, usually focused on distant galaxies, turned its sensors toward the asteroid belt. Even amateur astronomers with backyard telescopes joined the effort, uploading their observations to shared databases. The global response was swift and coordinated. Yet beneath the scientific collaboration, an undercurrent of unease began to build. By March 15th, preliminary spectroscopic analysis added another layer of mystery. The light signature reflected from 31 Atlas contained absorption lines that didn't match known asteroid compositions. Every rocky body in the solar system carries a chemical fingerprint, elements forged in ancient stellar furnaces and preserved across billions of years. These signatures are as reliable as DNA evidence. 31 Atlas showed traces of rare earth elements in concentrations never before detected in natural space objects. Lanthanum, europium, and terbium appeared in ratios that some researchers privately described as impossible. The data was cross-checked and verified by independent teams. The results remained consistent. Something about 31 Atlas violated the expected chemistry of solar system formation. One planetary scientist, speaking anonymously to colleagues, suggested the composition resembled materials processed through industrial refinement rather than natural cosmic evolution. The comment, though speculative, captured a growing sentiment within the research community. This object didn't fit the patterns established by decades of asteroid study. Music. As more telescopes locked onto 31 Atlas, its orbital characteristics revealed another puzzle. Standard calculations predicted a stable, elliptical path consistent with gravitational mechanics. But by March 20th, tracking stations noticed something unexpected. The object's velocity was changing in tiny, measurable increments. Asteroids don't accelerate on their own. Their paths are governed by gravity and inertia, unchanging unless disturbed by collision or gravitational encounter. 31 Atlas was alone in empty space, yet speed was increasing. The change was subtle, mere meters per second over days, but it was real and it was consistent. Mission control centers began running simulations. Could solar radiation pressure account for the acceleration? The calculations said no. Could outgassing, like a comet releasing frozen volatiles, explain the velocity change? The spectroscopy showed no signs of sublimation, no tail, no coma. Every natural explanation was tested and found insufficient. The object was moving faster than it should, and no known force could account for it. Engineers familiar with spacecraft propulsion quietly noted that the acceleration profile matched what one might expect from low-thrust ion engines. The observation was not published. It circulated instead through encrypted emails and late-night conference calls. By the end of March, 31 Atlas had become the most scrutinized object in the solar system. Research teams worked in shifts, maintaining continuous observation as the object moved through its orbit. Universities competed for telescope time. Data repositories swelled with measurements, spectra, and positional updates. Yet, despite the flood of information, something else was happening in parallel. A pattern of silence was forming around the most significant findings. Press releases emphasized the scientific excitement of studying a unique asteroid. They mentioned the collaborative international effort. They celebrated new techniques in remote sensing, but they did not mention the anomalies. They did not mention the acceleration. They did not mention the chemical impossibilities. Music, the public remained largely unaware. Mainstream media carried brief stories about a newly discovered asteroid, framing it as another success for astronomical survey programs. The coverage was polite and forgettable. Meanwhile, within closed scientific forums and private communications, the tone was different. Researchers began using careful language, hedging their observations with caveats and uncertainties. Some noted the pressure to avoid speculation. Others mentioned quiet requests from funding agencies to delay publication until more data could be gathered. The phrase "more data" became a recurring refrain, an excuse for postponement that seemed to stretch indefinitely. By early April, independent analysts began noticing discrepancies. Amateur astronomers, tracking 31 Atlas with their own equipment, compared their measurements to official reports and found gaps. Certain observation windows went unreported. Specific wavelengths of spectroscopic data were omitted from public databases. When questioned, institutional spokespeople cited technical difficulties, calibration issues, or data quality concerns. Each explanation sounded reasonable in isolation. Together, they formed a pattern of selective disclosure that left more questions than answers. What began as a routine asteroid discovery had transformed into something else entirely. 31 Atlas was raising questions that reached beyond astronomy into territory few scientists wanted to openly explore. The object's behavior, composition, and the response to its study suggested a story more complex than any press release revealed. As April progressed and observations continued, the scientific community found itself caught between curiosity and caution, between the drive to understand and the instinct to contain. On April 12, 2025, NASA announced a joint task force with the European Space Agency and the Japan Aerospace Exploration Agency to conduct what they called a comprehensive study of 31 Atlas. The announcement was made through a carefully worded press release that emphasized scientific cooperation and cutting-edge observation techniques. It promised unprecedented access to data from multiple space-based platforms and ground observatories. The language was optimistic, the tone professional. But for those paying attention, the formation of such a high-level task force for a single asteroid raised immediate questions. Why this object? Why this level of coordination? And why now? The task force included some of the most respected names in planetary science, but also specialists whose expertise seemed oddly specific for an asteroid study. Materials engineers, astrobiologists, even a theoretical physicist known for work on exotic propulsion systems. The roster suggested a scope far broader than routine asteroid characterization. When journalists inquired about the unusual composition of the team, official responses stayed vague. We're taking a multidisciplinary approach. We want to explore every avenue. The object presents unique research opportunities. Each answer deflected rather than explained. Music. By mid-April, the observation campaign intensified. The Hubble Space Telescope was repositioned for extended monitoring sessions. The James Webb Space Telescope allocated precious observation time, normally reserved months in advance for deep space surveys. Ground-based interferometer arrays in Chile and Hawaii coordinated simultaneous observations, creating synthetic apertures capable of resolving details smaller than any single telescope could achieve. The resources being devoted to 31 Atlas were extraordinary, yet the public data releases remain sparse. Weekly updates contain measurements of position and brightness, but little else. The spectroscopic data that had revealed the unusual elemental composition was conspicuously absent from subsequent reports. Independent researchers began compiling their own observations, pooling data from amateur networks and smaller observatories not bound by institutional protocols. What they found added new dimensions to the mystery.
The probability
Several
of
observers
impact on the
noted that
secondary burn
31
is
Atlas
increasing.
appeared to be rotating,
We need to adjust the
but
maneuver
its rotation
parameters
rate
now,
was
or we lose
inconsistent
the
with
window.
observed brightness variations. A tumbling asteroid should show periodic changes in reflected light as different surfaces face the sun. 31 Atlas showed patterns that didn't match simple rotation. The brightness changes seemed too regular, too precise. One analyst described them as geometric rather than chaotic, a distinction that implied something other than random tumbling. Music. On April 23rd, a research paper appeared briefly on an open-access preprint server before being removed within hours. The paper, authored by a team at European University, presented detailed analysis of 31 Atlas's thermal emissions. Infrared observations had detected heat signatures that didn't correspond to solar heating alone. The object's temperature distribution was uneven in ways that suggested internal heat sources. Natural radioactive decay could account for some warmth in large asteroids, but 31 Atlas was too small for that mechanism to produce the observed temperatures. The paper proposed several explanations, each hedged with uncertainty, before concluding that more investigation was needed. By the time the broader scientific community noticed the paper, it had vanished. Queries to the authors went unanswered. The university declined to comment. The removal of the paper did not go unnoticed. Screenshots and cached copies circulated through social media and specialized forums. Science journalists began asking questions. Why was the paper pulled? Was the data flawed? Had the authors made an error? The university eventually released a brief statement saying the paper was withdrawn for additional peer review and would be resubmitted after revisions.
We have an anomaly.
The explanation
Check the coordinates
satisfied
now.
no one. Researchers familiar with academic publishing noted that voluntary withdrawals for revision are common, but usually come with author statements. This withdrawal was silent and sudden. The timing felt less like scientific caution and more like suppression. Music. As April turned to May, the task force held its first public briefing. The event was streamed live, and the turnout was significant. Thousands of viewers tuned in,
thrust from
expecting
the gas jets
clarity on the mounting questions surrounding 31 Atlas.
F1 and
The
F2.
briefing opened with presentation on the observational campaign's scope and technical achievements. Graphs displayed orbital tracking precision. Charts showed spectroscopic coverage across multiple wavelengths. The speakers highlighted international cooperation and the valuable scientific returns from studying rare asteroid types. The tone was congratulatory, the content technical but unrevealing. When the briefing moved to questions, the atmosphere shifted. A reporter asked directly about the unusual elemental composition detected in early observations. The lead scientist paused, then replied that initial readings are often subject to calibration errors and that refined analysis was ongoing. Another question addressed the thermal anomalies mentioned in the Withdrawn paper. The response was cautious. We're aware of various independent analyses. Our team is reviewing all available data. Thermal modeling of small bodies is complex and requires careful validation. The pattern established itself quickly. Every specific question met a general answer. Every anomaly acknowledged was immediately cushioned by reminders of complexity and the need for patience. One question broke through the careful choreography. A science blogger, granted access through a press lottery, asked why the task force included propulsion specialists if 31 Atlas was simply an asteroid. The room went quiet. The lead scientist shifted in a seat, glanced at colleagues, then offered a measured response. Our team includes diverse expertise to ensure we consider all possibilities. Unusual objects require unusual approaches. The answer explained nothing while confirming something. The choice to include
Galaxies are
propulsion
not spread
experts was
evenly,
deliberate,
but clustered
and the
along
reasons for that
glowing
choice remain
filaments of the
classified
cosmic
as
web.
pending further study. Music. The briefing concluded with promises of future updates and assurances that all findings would eventually be published through proper scientific channels. Viewers were reminded that space science moves slowly, that peer review takes time, and that premature conclusion served no one. The final words emphasized patience and trust in the scientific process. But the subtext was impossible to ignore. The task force was asking the public to wait, while withholding the very information that would justify that wait. The disconnect between the scale of the effort and the meager explanations offered left many feeling that the real story was being told in what remained unsaid. By early May, 31 Atlas had completed nearly a full orbit since its discovery. Tracking data confirmed that its acceleration had not only continued, but had become more pronounced. The object was now moving measurably faster than gravitational models predicted.
The way the golden hour hits this
Some
building
calculations
is
suggested the
incredible.
velocity change was equivalent to a continuous thrust.
Are you
of
heading back to
several
the
newtons.
dorms now?
Tiny by spacecraft standards, but impossible for an inert rock. Engineers who worked with ion propulsion systems recognized the signature.